So let us consider some particular case of a shallow potential well. So again, recall that we are dealing with a Schrödinger equation. In the physical units, it reads as follows. And for the sake of simplicity, from now on, we will take h bar equal to m and equal to 1. And in the remaining formulas, we will just remove these factors everywhere. So the Schrödinger equation simplifies. So it's just 1/2. For the rest, recall that we are dealing with a problem stationary state in some potential u of x, which is assumed weak in a certain sense. And now we will consider some specific case of u of x given by the following equation. So it's minus u naught over 1 plus modulus x over a. So this is a potential well which has a certain cusp in the at x equal to 0. What is actually even more important is it's quite slowly decaying function of coordinate. So let us rewrite this equation in the following form. So explicitly it takes the following shape. And here I made explicit the fact that energy corresponding to eigensolution of this equation is negative, so it's convenient to separate explicitly this sign and write down the modulus sign here. And we are looking for, remember that spectral equation for Schrödinger equation is, spectral problem for Schrödinger equation is to find such energy E that this equation, differential equation, has a solution which is normalizable. That is, integral of psi squared dx is finite. That is, it converges. And recall that in the previous lecture we discussed some approximate formula of, which should be familiar to you from quantum mechanics course. And if not, take a look at its derivation. And this formula reads again in these units where h bar and m are equal to 1. This formula reads this formula gives approximate expression for the energy of the ground state in such a weak potential well. So it's approximately equal to minus 1/2 integral of u of x dx from minus infinity to infinity, and the integral is squared. So this formula is valid for weak potentials. So let us try to apply it for a given case and try to estimate what would be the ground state energy in such a potential. So imagine it's somewhere here, so it's negative, and let's try to estimate it. So we expect that this energy should be given by the following expression. From minus infinity to infinity squared. And obviously, already in this stage, we see that this standard textbook formula breaks down. And the reason for this breakdown is that the integral, this integral in the square bracket actually diverges. So let us make some rearrangement of this equation, and more or less it is minus u naught squared over 2, and the integral is taken from even function of coordinates, so it can be written as 4 integral 0 infinity dx or 1 plus modulus x over a squared. Now, after we have factored some numbers and constants, we are left with this single integral, which apparently generates a lot of problems. But in fact, we may recall that the origin of this equation, and the origin of this equation is such that actually this integral was obtained assuming that wave function does not change drastically on the scale where this integral converges. And we see that problem comes from the fact that actually in this situation the integral actually diverges. So this approximate is not legitimate. And the most naive approximation, which is, I would say, a matter of physics, but later we will derive it more formally by solving this differential equation. But if we use our physical reasoning, we understand that this integral should actually be cut off at typical scale characteristic for the corresponding wave function. And this gives us straightforward estimate. So this, we expect that this integral should be of the order of we see that would this integral converge, then it would be proportional just to A, to characteristic scale of the potential. Since it diverges additionally, in addition to A, it actually provides a certain logarithmic factor, which should be squared. And inside the logarithm, there is a factor which this square root of 2 energy is just characteristic special scale of the wave function. So wave function of the localized state will have a certain scale, which is determined by the energy. And so this comes to this log. As long as this physical style reasoning is not very convenient to you, just have in mind this answer, and it will guide us for the solution, for the more accurate solution, which will be obtained by an analysis of this differential equation. But for now, let us see that we were somehow able to derive, note that we have energy which is both in the left-hand side and in the right-hand side of the same equation. Of course, this equation is transcendental one and cannot be solved exactly, but in certain limit, when potential is small enough, the energy can be estimated as follows. This is so-called logarithmic accuracy, which is standard for physical analysis. And this is kind of iterative solution. So in the first stage of the solution, we neglect a logarithm at all, and then we estimate energy to be just minus 2 u0 squared a squared, and then we try to improve this accuracy and substitute the just calculated value inside the log. So this gives us and this can be further simplified. And please have in mind that in performing this estimate, we have assumed that potential is weak. In practice, it means, of course, for a given problem, it means that the following parameter is a small number, which means that here the logarithm is large and the energy is slightly enhanced by this logarithmic factor. So again, just to reiterate, we have used this physical reasoning just to get some guess for the actual result of the solution of the differential equation. And now, armed with this guess, we will do our best to actually solve this differential equation and obtain spectral equation for energy, and then solve it numerically or analytically in some limits. And this is the goal of the remaining part of this lecture.